Hey guys, my name's Aaron. Here's gonna be my student ID. It's gonna be 247700618. And right now I'll be talking to you guys about our LCD function as well as our UARTs. So just for starters, I can start with our first function. It'll be our LCD send data byte function. This function actually allows us to send data bytes into our LCD. This includes characters, symbols, and numbers and stuff like that. Our LCD send command byte function actually allows us to send commands, instructions. This actually allows us to control the behavior of the LCD, such as to turn it off, display on, display off, as well as to like set the cursor and stuff like that. And then we have our set cursor function, which will take two parameters. It's going to be our rows and columns, and will actually allow us to select where we want to be printing our strings on the LCD, as it's 16 by 2. And we have a send string function. This is pretty self-explanatory. All it does is converts the string variable. It increments to each character, and it will send using the send data. It will send each character to the LCD. And we have our state A LCD function, which allows us to to display the state A LCD, which is going to be our street number as well as the Mechatronics. These can be configured using our set cursors, as the first numbers here will be the different rows. That's why we have them as different, 1 and 0. And we have our state B LCD function, which allows us to actually display the ADC values by the potentiometer. As you can see, we only change one of the rows, as we leave the bottom as Mechatronics 1. And finally, we have our LCD init configuration function. This function only occurs once, which is going to be right here. Right here. And it occurs only once, and it allows us to actually set up the LCD. We can use this little flow chart here to actually set it up, as it will tell us what bits, whether it's the upper nibble or the lower nibble, and allows us to set it up along with these delays, which will correspond to whatever it says in the flow chart. Hey guys, now I'm going to be talking about the UART serial function. We were actually unable to get the serial print to stop for the keyboard input. I was actually able to get it to stop when I pressed the letter S, but I wasn't able to let it continue. So yeah, so we didn't end up integrating it into our system. Instead, we just have this. We just have it printing every 0.5 seconds using our timer 16 as our clock. And it'll be printing this message right here with the ADC reading updating to whatever the potentiometer will be reading. So yeah, that's all we got. And just to show a demo as well, as of right now, the system is in state A, as like the serial monitor is printing, and then it shows that state. And then when you press the button, it switches to state B, and the printing should stop right there. And then if you adjust the potentiometer, it will adjust the ADC value on the LCD monitor, and it's not printing on the serial monitor. But when you press the button again, it switches back to state A and continues to print on the serial monitor. So there you go.
Hello, my name is Daniya Syed. My student ID is 247855521, and I'll be explaining how we got the servo to be controlled by the potentiometer. The servo motor is controlled by the potentiometer through a series of steps in the code. First, the analog voltage generated by the potentiometer is read by the microcontroller's analog to digital converter, ADC. This analog voltage is then converted into a digital value indicating the position of the potentiometer. This digital value is mapped to an angle ranging from 0 to 180 degrees. For this code to be successful, a range of different functions were created. The right angle to servo function takes an angle value as an input, maps it to the corresponding PWM cycle, and then sets the duty cycle to control the position of the servo motor, effectively positioning it according to the input angle from the potentiometer. The map function scales a value from one range to another. In this code, it's used to convert the analog input, ranging from 0 to 4095, to the angles of the servo, which is the range from 0 to 180 degrees, and the PWM duty cycle range 500 to 2500. Calculations were done to find the prescaler and auto-reload register values for the servo, which were used to set the mapping.
Hi, my name is Zain Khan, and this is my student ID. I'll be explaining the blinking LED within our state machine for the MCU demo. So in order to blink the LED at varied frequencies, we needed to undergo certain steps. The first step was to, within the IOC configuration, configure timer 3, which will be used almost as like a Millis counter that kind of counts up and down depending on whether we need certain actions to happen in a time state. So we went into the configurations tab as shown here, and we configured the PSC and ARR values to their respective necessary values. So this was 15 for PSC and 19999 for the ARR. And this corresponds to a frequency of 1 Hertz. So basically, every millisecond we can have an incremental counter, which is helpful because we can then turn on the LED for a certain amount of times or turn it off. And so you can see this function here, which is basically our interrupt function, where every millisecond it will add 1 to our millis counter, which is just a variable, an integer variable. And so we can use this millis counter, as I explained earlier, to then blink the LED for certain periods of time. The next part of our function was actually using the potentiometer to actually vary the frequency. And in order to do that, as you can see in the configuration, we configured ADC to in0, and this allowed for the PWM channel to kind of flow through. And that means that every time we turn the potentiometer, it changes the ADC value. And we can map that ADC value to the frequency needed for the LED, and you can see that there. So with this mapping, we can then specify an integer called period. This period is basically the time that it's off or on by. So 500 milliseconds will correspond to 5 hertz, and then 100 is 1 hertz. And so we kind of vary the potentiometer reading. As we turn the potentiometer, it'll then vary the frequency. And our overall demo for that flashing frequency can be seen here. So as you see, as I turn the potentiometer, it varies the frequency, but it also allows that servo to move, as Daniya explained earlier, using her own mapping functions and that write to servo controller. So with this one ADC value, we can vary a lot of different things, whether that's the LEDs, whether that's the servo, or the LCD display that Aaron explained as well. So that's pretty much an explanation of how we varied our LEDs with the frequency.
Hi there, my name's Isabelle Tia, and this is my student ID number, and I'll be demonstrating and explaining our system state machine for you. So with our state machine, we utilize an external peripheral interrupt function, which has been integrated into our push button 2 to toggle between A and B. So this flow diagram represents the overall system and interactions between state A, B, and C by toggling push buttons 1 and 2. So with our system, we were able to toggle between states A and B where we initialize a variable called button pressed as 0. This variable acts as a way to shift between states A and B. So in our main loop, when the button is triggered, the variable push button pressed is updated to a 1 to shift to state B, else it'll stay in state A as button press remains as a 0. An attempt was made for state C. So we were able to connect the UART-TX pin to an external LED, which allowed us to configure the push button to toggle between state A and C. So when the push button is pressed in state A, it switches to state C, where the LED flashes at 1 Hz for 3 times, but it was not able to revert back to the initial state.